Welcome to our tutorial on solving a system of equations by graphing. In this lesson, we are going to explore estimating the different possible solutions for a system. We will be graphing lines frequently throughout the lesson, so be sure to review the lessons on graphing lines if you need to before proceeding with this lesson. First, let's recall the three possible solutions for a system of linear equations. First, the most common possibility is when the two lines intersect at a point. The second possibility is that the lines are parallel. There is no solution because the lines do not intersect. The third possibility is that the two equations actually represent the same line. There are an infinite number of solutions. We can say these lines coincide, or they are coincident or coinciding lines. So let's try estimating the solution to the system of equations 3x minus 2y equals 6 and y equals 1/2 x plus 1. First, we'll graph 3x minus 2y equals 6 by finding the intercepts. To find the y-intercept, we substitute 0 in for x and solve to get y equals 3. This means our y-intercept is the point 0, -3. Then we substitute 0 in for y to find the x-intercept, 2, 0. Once we have both of these points plotted, we can graph our first line. Next, we'll graph the line y equals 1/2 x plus 1, which is in slope-intercept form. We can see the y-intercept is the point 0, 1 by looking at the constant term, positive 1. Then we can see that the coefficient of x, 1/2, is the slope. This means that we can start at the y-intercept to rise 1 and run 2 to find a second point, 2, 2, that's on the line, and graph the line. Now that we have both lines graphed, we can look for the intersection point, which in this case is the point 4, 3. If we want to verify this approximate solution algebraically, we simply have to substitute x equals 4 and y equals 3 into both equations to see if they work, which they do. Finally, I want to examine the other two possible solutions. First, we'll look at the case where there is no solution using the system of equations 3x minus 2y equals 6 and y equals 3/2 x plus 1. Notice 3x minus 2y equals 6 is the same line we started with in the first example, so you can see it's graphed the same way as before. Next, we'll graph the line y equals 3/2 x plus 1, which is in slope-intercept form. We can see the y-intercept is the point 0, 1 by looking at the constant term plus 1. Then we can see the coefficient of x is 3/2. This means we can start at the y-intercept and rise 3 and run 2 to find our second point, 2, 4, and graph the line. It appears as though the lines are parallel, which we can confirm algebraically by examining the slope of our first line more closely. Using the 2 points we found, we can see that its slope is 3/2 as well, because we have to rise 3 and run 2 to get from one point to the other. One property of parallel lines is that they have equal slopes. These lines will never intersect because they are increasing at the same rate. Therefore, there is no solution. For our final example, we'll look at the case where there is an infinite number of solutions using the system of equations 3x minus 2y equals 6 and y equals 3/2 x minus 3. Again, 3x minus 2y equals 6 is the same line we started with in the first example, so it's graphed the same way as before. Next, we'll graph the line y equals 3/2 x plus 1, which is in slope-intercept form. We can see the y-intercept is the point 0, -3 by looking at the constant term, negative 3. Notice this point is on the other line. Then we can see that the coefficient of x, 3/2, is our slope. This means we can start at the y-intercept and rise 3 and run 2 to find a second point, 2, 0, which is also on the other line. The famous geometer Euclid states in his first postulate that 2 points determine exactly one line. Since these lines share 2 points, we know they are the same line, meaning there are an infinite number of solutions to this system. Now that you've seen some examples, try some of the activities to solve systems of equations by graphing on your own.